Vectors in the plane, day 2. First, let's talk about unit vectors. So if the magnitude of a vector is 1, then v is called a unit vector. Now, the way this is written, though, I didn't exactly read it identically. It just says the magnitude of vector is 1 if and only if v is a unit vector, which means that you say if it's a unit vector, then the magnitude is 1, and also the other way around. If the magnitude is equal to 1, then it's a unit vector. That's how those if and only if statements work. Now, if the magnitude of a vector is 0, or rather, the magnitude of a vector is 0, if and only if v is a 0 vector. You can make any vector a unit vector by dividing it by its own magnitude. So let's do that in this first example right here. So find a unit vector in the same direction of vector v, -2, 5, and verify that this result has a magnitude of 1. So the first thing that we need to do is find the magnitude of vector v. So that's just going to be the square root of -2 squared plus 5 squared, which is the square root of 29. Now we're going to take vector v and we're going to multiply it by 1 over the square root of 29. So times, this is my pointy bracket here, -2, 5, close my pointy bracket. And then we can multiply that 1 over 29 through there. We'll get -2 over the square root of 29, 5 over the square root of 29, pointy bracket. Now we could give this vector another name, I don't know, call it vector A or something like that. And then they want us to verify the magnitude. So we're going to do verify that's equal to 1. So the magnitude of vector A, that's going to be the square root of -2 over the square root of 29 squared plus 5 over the square root of 29 squared. The square root of, when you square fraction, square the top and the bottom, so it's going to be 4 over 29 plus 25 over 29. Holy smokes, that's the square root of 29 over 29, which is, you know what that is? Yep, that's equal to 1. Voila. So we did two things. We found the vector that has the same direction as vector v, but this particular vector has a magnitude of 1. Okay, so what we're going to be talking about today is how you can write different forms of vectors. There's unit vector form, and then there's another form we're going to talk about later called trig form, also known as polar form. We've already talked about component form, so these two are new. So again, with the unit vectors, let's say that we had a vector that had components 1, 0. If we wanted to find the magnitude of that, it would be the square root of 1 squared plus 0 squared, which is the square root of 1 squared, which is 1. Let's draw this one. So it's going to start at, we're in standard form. So this vector is in standard form. It's going to start at the origin, and it's just going to go to the point 1, 0. That's it. Not a very exciting vector, but that's the vector, okay? Just sort of right there on top of the x-axis. So this is the thing. This particular vector is a very special vector. This vector is called the standard unit vector, and its name is vector I. It's a special vector with a standard unit vector that's called vector I. You see it here in the picture. Now also in the picture, you see another special standard unit vector, that's vector j. The component form of vector j is 0, 1 in pointy brackets. So these unit vectors become very useful because you could write any vector as a multiple of these standard unit vectors, and we're going to do that today. Now, one thing before we move on, I want you to notice how the I must be written in bold to distinguish it from the imaginary number I. And when we type the imaginary number I, we tend to use an italicized lowercase I. But here for our standard unit vector, we're using a bold I. And then when you handwrite the imaginary number I put a little hook on my lowercase I there. It looks a little bit like a backwards J, but I don't have the nicest handwriting. Okay, so I already said that these standard unit vectors can be used to represent any vector that's written in component form. So for example, let's say that I have vector v that has component form 4, -5. Okay, so this is showing you that unit vector form is v sub I, which is the x component of the vector, times vector I plus, there's a comma there, shouldn't be there, v sub 2 times the standard vector j. So if I go back to this 4, -5, this means that I could write this as vector v, I could call this 4 times vector I minus 5 times vector j. So let me show you why those are the same thing. If I actually substitute vector I, so that's going to be 4, and then vector I was 1, 0 in pointy brackets, minus 5 times 0, comma 1 in pointy brackets, that's vector j. Then the 4 and the negative 5 are scalars, so I'm going to multiply the 4 through multiscalar multiplication, so it's 4, comma 0. And I'm going to leave this as a minus sign and call that 0, comma 5 in pointy brackets. And then remember, when we're subtracting vectors, we subtract their components. So 4 minus 0, and then 0 minus 5. So that's going to become 4, comma negative 5. So there you can see the connection between a vector in component form and then a vector in unit vector form. Sometimes unit vector form is known as the linear combination of vectors I and j. I find that name to be a little bit bulky. It's like too many syllables and too many words. So I like to call it unit vector form. So let's have a look at vector u is the vector with the initial point 2, comma 5. Notice our parentheses here, and the terminal point negative 1, comma 3. We have a sketch of the vector here on the right of the screen. We're going to write u in unit vector form. Now, because we're given just the coordinates of the beginning point and the end point, we need to first convert it over to component form. So vector u will be the end point, or the x component of the end point, negative 1 minus 2, comma 3 minus negative 5. Close this pointy bracket. So that simplifies to be negative 3, comma 8. Okay? So that's the answer in component form. And then in unit vector form, we can say that vector u is simply negative 3 times vector I plus 8 times vector j. There it is. Direction angles. So not only can we find the magnitude or the length of a vector, but we can also find the angle of the vector. Sometimes this is called the direction angle, or sometimes just angle. This should look kind of familiar when we did this with the unit circle. Do you remember something called reference angles? It's basically the same thing as reference angles. In quadrant 1, your direction angle is simply whatever angle the vector makes with the x-axis there. If your vector component form, so standard position, if it's in standard position, if it's in quadrant 2, then the direction angle is going to be that obtuse angle there. And then this angle right here, which I'm now calling that theta prime, that's like your reference angle, basically. Well, we're still going to call it the reference angle. If your vector in standard form is in quadrant 3, then this large angle here becomes your direction angle, but then the angle between the x-axis and the terminal side, or the vector rather, is the reference angle. And then finally in quadrant 4, you got your reference angle there, and then that angle, again, just like in the unit circle, moving in a counterclockwise direction, that would be the direction angle of the vector. So here's what's brilliant about it. If you have, let me draw a little picture here. If you have a vector, then let's do this in quadrant 1. So if you have your horizontal component, that's A, and your vertical component is B, and you're trying to find angle theta, well, from the point of view of theta, B is the opposite side, and A is the adjacent side, so that should make you think about the tangent from SOHCAHTOA. So the tangent of the angle is equal to B over A. Now, technically, when we do this, this is going to be like the tangent of theta prime is going to be B over A. We'll get to it when we talk about an example. And then, of course, there is a condition that, of course, A cannot be equal to 0 because thou shalt not divide by 0. All right, let's take a look at example number 3. We want to find the magnitude and the direction angle for the vector whose initial point is 4, 5, and terminal point is 2, comma 2. So first, let's find the component form. We'll call it vector v, give it a name. So that's going to be 2 minus 4, comma 2 minus 5. Remember, you always have to do the terminal point minus the initial point. So that is negative 2, negative 3. The magnitude, we've done that already, is going to be the square root of negative 2 squared plus negative 3 squared. So that's the square root of 13. Okay, that was part of our question, and there's our answer. They also want us to find the direction angle. So for the direction angle, let's think about what quadrant we are in. Negative 2, comma negative 3. If that vector were in standard form, what quadrant would you be in? Well, you would be in quadrant 3. When you're naming quadrants, you should always use a capital Q and capital Roman numerals. That's how we name our quadrants. So I'm going to say then the tangent of theta prime, this is going to be my reference angle. And when I do the reference angle, I'm going to ignore the negatives. I'm just going to say 3 over 2. I'm going to go to my calculator, and I'm going to do the inverse tangent. I need to make sure I'm in degree mode, because we're going to do these in degrees, of positive 3 over 2. And my calculator is going to give me 56.2 .3099 degrees. That's just a reference angle. Let me draw a picture to show you what I'm talking about. Okay, here is my vector in quadrant 3 that has components -2, -3. This angle here is actually theta, and that's obviously going to be bigger than 180 degrees. But what I want to do, because my calculator is not going to give me a response of 180 degrees, I need to find this angle here, or rather I just found that angle right there, theta prime, to be that 56-degree number. That theta is going to be 180 degrees plus the 56.3099 degrees. So you'll recall when we did reference angle that the rules for how you find the theta are different depending on the quadrant that you're in. So this angle turns out to be 236, and we'll just round to one decimal place, 236.3 degrees. Example 4, same thing. We're going to find the magnitude and the direction, but this time we're given the vector in unit vector form. So I encourage you to pause the video and try this one on your own. Okay, define the magnitude. Vector u is the magnitude of vector u, so put the bars around it, is going to be the square root of 3 squared plus -1 squared. If you need to write down the component form, you can. It's going to be pointy bracket 3, comma, -1. So that's going to be the square root of 10. So that's the magnitude. So that was part of the question, and that's the answer. Then for the direction angle, we need to think about what quadrant we're in. So 3, comma, -1, that is going to be in quadrant 4. So I'm going to say, first I'll find the reference angle. So the tangent of theta prime is going to be 1 divided by 3. I'm ignoring the negative. I always ignore the negative when I find my reference angle. I go to my calculator. I get that theta prime in this case is 18.435 degrees approximately. And since I'm in quadrant 4, sometimes it helps to draw a picture. So there's my vector in quadrant 4. It has horizontal component 3, vertical component -1. This large angle here, that's going to be more than 270 degrees and less than 360 degrees. That's the angle, my direction angle that I want. What I've just found, however, is the reference angle there. That's my theta prime, and that worked out to be 18.435 whatever degrees. And so you can see that in this situation now, theta is going to be 360 degrees minus 18.435 degrees, which is going to be 341.6 degrees. All right, let's consider something different. What if we were given a vector and we're told about its magnitude and we're told its angle, and now we want to find the component form? So in this example, I'm talking about a vector that has a magnitude or a length of 3, and it has a direction angle of 30 degrees, always from the positive x-axis moving counterclockwise. And we want to find the component form. In other words, we want to find its horizontal component and its vertical component. Let's put some letters on here. Let's say that the horizontal component is v sub 1. So that's going to be that distance there. And then v sub 2 would be that distance there. How in the world are we going to find, say, v sub 1 when we have that length is 3 and that angle is 30 degrees? Are you screaming SOHCAHTOA right now? Well, you should be, because you're right. We're going to use SOHCAHTOA. So from the point of view of the 30 degrees, v sub 1, that's the adjacent side, and then the 3 is the hypotenuse. So adjacent hypotenuse, you think cosine. So the cosine of 30 degrees would equal v sub 1 divided by 3. And then trying to find v sub 2, well, that's opposite the 30 degrees. So we can say then that the sine of 30 degrees is v sub 2 divided by 3. And then if I wanted to isolate this equation for v sub 1, I just multiply by 3. So 3 times the cosine of 30 degrees is equal to v sub 1. And 3 times the sine of 30 degrees is equal to v sub 2. Well, with vectors, we do, v sub 1, comma, v sub 2 in our pointy brackets. We're just going to call this 3 times the cosine of 30 degrees, comma, 3 times the sine of 30 degrees in our pointy brackets. But since they both have the 3, that's like your scalar. So let's take that 3 out. And then we have 3 times cosine of 30 degrees, comma, sine of 30 degrees. So what was this? The 3, that was your magnitude. The 30 degrees, that was your angle. So that leads us to what is known as the trig form or polar form of a vector, where the vector v can be equal to the magnitude of the vector times the components of the cosine of the angle, comma, the sine of the angle. Now, why is it called polar form? Well, we'll learn that later when we talk about polar graphs and polar coordinates. There is an alternate form for the trig form or the polar form, which is really like a combination of the trig form and the unit vector form. And it looks like this. The absolute value of vector v, and then the cosine of theta times vector I plus the sine of theta times vector j. I find this alternate form to be a little cumbersome because you've got like all these parentheses and you've got the plus sign and you have to put the little arrow above the I and the J. I think this one up here is a little cleaner, but I point this out because you might see the alternate form if you're looking online or you're hanging out on a Friday night and you're reading about vectors. All right. Number 5, this vector we're given the magnitude is 6, the direction is 300 degrees. We're going to write the vector in trig form, and then we're going to convert it over to component form. So we just talked about the trig form. Let's give our vector a name. We can call it u, and that's just going to be the magnitude of 6 times, pointy bracket, cosine of 300 degrees, comma, sine of 300 degrees. And that's it. That's the trig form. Next, we want to now turn that into component form. Can you guess how we're going to put that in component form? Are you saying to find the cosine of 300 degrees? I can hear you. I know you are. So for part B, we can say vector u is equal to 6 times the cosine of 300 degrees is 1/2 times the sine of 300 degrees, which is negative square root of 3 over 2. And then look at that 6. That's a scalar. So we can just multiply that scalar through there. So we're going to have then 3, comma, 3, negative 3, the square root of 3 in pointy brackets. And that's it. That's your vector in component form. Now, you might be wondering, what if you were given an angle that was not something that we knew from the unit circle? That's okay. It happens all the time. It happens quite a lot, actually. And all you'll do is you'll just go, if this was like, say, 301 degrees, just go to your calculator, make sure it's in degree mode, and do cosine 301 degrees, and write down the angle with the 2 or 3 decimal places. Voila. Now, we're going to go backwards. We have our vector in component form, and we want to find the same vector in trig form. So remember, to write it in trig form, we need the magnitude and we need the direction angle. So it's not unlike what we've already done, except now we're going to take it to another level by putting it in the trig form. So if you want to pause the video and go ahead and find the magnitude and the direction, that would be a great idea. The magnitude of vector m is going to be the square root of negative 12 squared plus 5 squared. That's going to be 13. The tangent of the reference angle is going to be 5 over 12. The reference angle is going to be 22.6199 degrees. This vector is in quadrant 2, so that means that we're going to take 180 degrees and we're going to subtract 22.6199 degrees. Feel free to draw a picture so you understand why we do that. And then that's going to be 157.380 degrees for my angle. So the information I need is that the magnitude is 13 and the direction angle is 157.38 degrees. So the trig form of vector m is going to be the magnitude times pointy bracket cosine of, let's just call this 157.4 degrees, comma, the sine of 157.4 degrees. And there it is. Our last example today. We have vector u in trig form. The magnitude is 7, cosine 80 degrees, sine 80 degrees. Vector v, the magnitude is 11, cosine of 125, sine of 125. We want to find the sum of vector u and v in trig form. What we will do is we will find the component form of each of these vectors, and then we will add them, and then we will find the magnitude of the new vector, the sum vector, resultant vector, as well as the direction angle of the resultant vector. To find vector u, the component form of that, that's going to be 7 times a cosine of 80 degrees, comma, 7 times a sine of 80 degrees. So that works out to be 1.215, comma, 6.8937. I just used my calculator to get those numbers. Now I'm going to do the same thing for vector v. All right, and those are my components there. Negative 6.3093, comma, 9.0107. Again, I just used my calculator to get those decimals. Now I need to add the two vectors, and I have negative 5.0938, comma, 15.904. I simply added the horizontal components, and then I also added the vertical components. Okay, now I would be finished if they wanted the answer in component form, but they wanted the answer in trig form. So we need to find the magnitude of vector u plus v. So to find the magnitude of vector u plus v, we're going to do the square root of the x component plus the squared plus the y component squared. So that gives us about 16.702. So that's the magnitude. And now we need to find the direction angle. So first, to find the direction angle, we're going to use the reference angle. So the tangent of the reference angle will be just positive 15.9 blah, 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 divided by the 5.09 blah, blah, blah. And that works out to be about 72.2410. That's my reference angle. But then we need to figure out in which quadrant is my sum angle, my resultant, my vector. And that is a negative value and then a positive value. So that's going to put us in quadrant 2. So somewhere in quadrant 2. So to find the angle theta when you're in quadrant 2, you need to do 180 degrees minus your reference angle. So that works out to be about 107.8 degrees. So we have our magnitude, we have our direction angle. So that's all we need to put in trig form. And so the trig form would just be 16.7 times the cosine of 107.8 degrees times the sine of 107.8 degrees. Voila.